Okay, so up to this point, if you've been watching the videos, you know exactly what I'm about to do. I'm going to underline all of my givens and circle what I'm looking for. Now, I just circled moles. Since there's moles in this problem, then we have to use the ideal gas law, the PV equals nRT, this one right here. Okay? So here, mmHg, if you're not sure what that is, first of all, it says pressure right here. Also, you can look on your variable chart like we have been doing. So this is going to be pressure. Volume of 31.0 liters. Temperature of 87 degrees Celsius. Now, just because this is the ideal gas law doesn't mean that changes the Kelvin rule. So you do need to add 273 to this, which will give you 360 Kelvin. All of the gas laws require Kelvin. And we're looking for moles, which we just said means we have to use the ideal gas law. So the ideal gas law is right here, PV equals nRT. And just like last time, if the moles didn't tip you off, the fact that you only have one of each volume should probably tip you off. Okay, we are looking for moles, so we're going to get moles by itself. We're going to divide by R and T. On both sides. R and T will cancel over here, so I will erase those. And now we have PV over RT equals N. And as I was doing this problem, I just realized that both of the ideal gas law problems I did, we were looking for something on this side of the equation. You can also look for pressure or volume, okay? So please don't get kind of thrown off by that. You can also look for these over here, and then you would just do the same thing. You would divide by whatever you aren't looking for and move on from there. So now let's go ahead and plug this stuff in. P is going to be 810 mmHg. mmHg stands for millimeters of mercury. It's like an old school way that they used to tell pressure before they realized mercury was very dangerous. 31.0 liters is our volume here. And then we will divide by both R and T. We need to find our value for R, so let's find our R table, okay? So here we have the different values for R. Again, you'd pick it based on the pressure, okay? So here, our unit for pressure is mmHg, which is right here. So we're going to use 62.4 as our value for R. I don't require that my students write the units for R in the expression. That's kind of a lot. So just know to use the units to find the value. And then our temperature is going to be 360. And then you just solve. Remember, if you're using a calculator, which I think you probably are, that you have to put these in parentheses when you do the division so that it divides correctly. So we do 810 times 31. So you should get 1.18 moles. And that's it. Last problem. Okay, so here we have a bunch of givens. So we're looking for final temperature. And now we're going to label all this stuff. So mmHg is going to be pressure. And we have one pressure and two pressures. Sometimes students ask me, how do I know what 1 and 2 is? You just read the question. Usually it is in order, but make sure you read the question because this says is reduced from, so that means it starts at 1200 and goes to 850. Just read the question, it gives you the context. And then volume is increased moving from, so if it goes from this one, that's V1, to this one is V2. What is the final temperature if the original was 90 degrees Celsius? So make sure you do your Kelvin conversion. So it's 363 Kelvin. All right, so here we have P's, V's, and T's. So we need to use the combined gas law. So the combined gas law is the only one that has multiple P, V, and T. So like I said in one of the other videos, a lot of times students get confused by combined versus ideal. Okay, so you know this isn't an ideal gas law problem because there's no moles in it. You also know that because you have multiple of everything. So you have multiple pressures, multiple volumes, and well, you have one temperature, but you're also looking for a temperature. So that has to be combined gas law. So the combined gas law is called that because you're pretty much just smushing all the other gas laws together except for ideal gas law. But Boyle's, Charles, Gay-Lussac, they all get smushed together so that they look like this. So just like I did with Charles and Gay-Lussac, I'm going to cross multiply to make this a little bit easier on us. So I'm going to do P1V1 times T2. Just be really careful with those T's. Make sure you know it's T2 that goes here. That's the point of cross multiplying. And then P2, V2, T1. And I really apologize to the teachers if you don't like the cross multiplying thing. But I always teach it this way, so you might need to make different videos. All right, so here we are looking for T2. what would the final temperature be if the original temperature was 90 degrees Celsius? So we're looking for T2. Now this looks a little weird because now we're looking for something on this side of the equation. Nothing changes. Everything is exactly the same. We have done problems up to this point that for whatever reason I was circling stuff on this side of the equation. It doesn't matter. Okay, it doesn't matter. So all you have to do is get T2 by itself. You divide by P1 and V1 on both sides. And these will cancel out, so we can go ahead and erase them, the P1 and the V1. And then we just plug stuff in, okay? Just be really careful when you're plugging it in, and it's exactly the same as all the other ones. You want to make sure you're putting P2, which is this one, and not P1, okay? Don't go in order. If you labeled everything at the beginning, you shouldn't have a problem here. So P2 is going to be 850. And then V2 was 0.350. And then T1 is 363. And then you divide by P1, which is 1200. And V1 was 0.085. And then you just go ahead and do that out, making sure that you have parentheses for the denominator at least. So you do 850 times 0.35 times 363 divided by 1200 times 0.085. So you end up with this, and that's for sig figs. If you do it on your calculator, you might get 1058.75. I'm just doing sig figs because actually, I just realized this one's different. Well, whatever. This is close enough to actually get the sig figs correct. You'd have to put in scientific notation, which I don't think we want to get into right now. Now, the question originally gave us the original temperature in Celsius, but it didn't specify that our answer needed to be in Celsius. So if you wanted to, you could put it in Celsius and subtract 273 from this number. But really, as long as the question doesn't make you convert it, you don't have to. We wanted you to convert it, we would specifically say what's the final temperature in Celsius. Okay, so that's it.